The NHERI Wall of Wind at Florida International University is an NSF-funded facility that enables researchers to better understand wind effects on civil infrastructure systems in order to prevent wind hazards from becoming community disasters. The NHERI WOW experimental facility is powered by a combined 12-fan system capable of repeatable testing and up to 157 mile-per-hour wind speeds. One advantage of the facility is the multi-scale and high Reynolds number simulation using 12 fans and a water spray system, which demonstrates the effects of wind and wind-driven rain. The 16,000 square foot fenced-off secure area enables researchers to plan and perform destructive tests for up to Category 5 hurricane wind speeds. Using a wide range of equipment, instrumentation, and experimental simulation protocols, the distinguished group of faculty, staff, and the well-trained team of technical and operations personnel are ready to support your world-class research. The Wall of Wind offers the following testing: high-speed holistic testing with simulated wind speeds, including Category 5 hurricane, destructive tests to study failure modes, wind-driven rain simulation to study water intrusion, full and large-scale aerodynamic aeroelastic testing in atmospheric boundary layer flows, extreme environment testing to develop innovative mitigation devices, and conventional boundary layer wind tunnel testing. If you are interested in learning more about the resources at the NHERI FIU Wall of Wind Experimental Facility and how they can support your research, contact Arindam Chowdhury. The Hinsdale Wave Research Laboratory was established at Oregon State University in 1972 with the construction of the Large Wave Flume. The lab is the largest nearshore experimental facility in the United States. Researchers from around the world use the facility to examine the effects of wave, wind, and coastal hazards on a variety of structures and coastal areas. The purpose of the research conducted at Hinsdale is to improve the resilience and sustainability of coastal areas as well as develop innovative solutions to the design of coastal infrastructure. The large wave flume and directional wave basin allow for researchers to explore coastal and nearshore processes, such as nearshore hydrodynamics, tsunami research, coastal structures, sediment suspension and transportation, environmental fluid mechanics, and floating structures. The lab also hosts collaborative projects. One such project, pictured here, is the Wave, Surge, and Tsunami Overland Hazard Loading and Structural Response for Developed Shorelines by Kennedy, Gainham, Barbosa, and Cox. This project created new tools to predict structural damage from inundation events along developed shorelines using computer-based predictive methods. Hinsdale also hosted the NSF Career Award research from Andrew Myers, which focused on advancing multi-hazard assessment and risk-based design to promote offshore wind energy technology. If you are interested in learning more about the resources at the Wave Research Lab at OSU, contact Hinsdale at oregonstate.edu.
The Design Safe Cyber Infrastructure is part of the NSF-funded Natural Hazard Engineering Research Infrastructure. It provides a web-based platform to enable transformative research that protects human life and reduces damage during natural hazard events, such as earthquakes, windstorms, and floods. As these events become more common and more destructive, Design Safe aims to amplify and link the capabilities of natural hazard researchers in the U.S. and abroad. The Design Safe Data Depot provides private and public disk space to support research collaboration and data publishing through a web interface. The Design Safe Reconnaissance Portal uses a map interface to provide easy access to data collected to investigate the effects of natural hazards. And the Design Safe Workspace provides cloud-based tools for simulation, data analytics, and visualization, as well as access to high-performance computing. There are many examples of how Design Safe data and tools are being used to enhance our understanding of the effects of natural hazards on the built environment. Detailed data and images of damaged buildings have been collected by many groups of researchers after events such as Hurricanes Harvey and Michael. These data have been published on Design Safe and are being used by the broader engineering community to better understand hurricane impact and to use artificial intelligence to better predict potential hurricane damage. To better understand the impact of a magnitude 9 earthquake on the city of Seattle, researchers at the University of Washington and the U.S. Geological Survey used design-safe computing resources to perform regional ground-shaking simulations. These simulations incorporate the unique deep sediment structure in Seattle, which affects the characteristics of shaking and can be particularly damaging to tall buildings. The results from these simulations are available via Design Safe and are being used in the design of high-rise buildings in the region. These are just a few examples of how the capabilities of Design Safe are enhancing natural hazards research and becoming an integral part of research discovery. Learn more or join our community at designsafe-ci.org.
Much of the world's population lives in regions susceptible to earthquakes, hurricanes, or other natural hazards where the risks are compounded by aging buildings and civil infrastructure that often are not designed to resist the hazards. While experiments and field observations are used to understand the impact on communities, computational simulations are an essential component of the science and engineering needed to evaluate and mitigate the potential devastating effects of natural hazards. To advance these capabilities, the NSF-funded Computational Modeling and Simulation Center, or SIM Center, serves the natural hazards community as an essential and central resource that provides next-generation computational modeling and simulation software tools, user support, and educational materials. The SIM Center's goal is to advance the nation's capability to simulate the impact of natural hazards on structures, lifelines, and communities. Headquartered at UC Berkeley, the SIM Center relies on a diverse team located throughout the country with expertise in structural and geotechnical engineering, computational fluid dynamics for wind and water, earthquake and wind engineering, performance-based engineering, social science, state-of-the-art computer science, and software development. The Sim Center addresses these diverse hazards and disciplines by producing flexible and reconfigurable software applications that researchers and practitioners can use to better understand the effects of natural hazards on the built environment. These applications enable the Sim Center to achieve these goals. 1. Provide tools to interface with outputs from the hazards science community. 2. Advance local-scale computational modeling of buildings and infrastructure subjected to natural hazards. 3. Facilitate regional-scale risk simulation with multi-fidelity, high-resolution models and data. 4. Develop tools for integration with social science and urban planning models. And 5. Engage and educate the natural hazards engineering community to advance simulation methodologies and their use. Emerging researchers are trained through workshops, webinars, and programming boot camps. The state-of-the-art in computational simulation is published in a recent report which includes how tools developed by the Sim Center incorporate advanced simulation methods, uncertainty quantification, cutting-edge artificial intelligence techniques, and high-performance computing. The report outlines how the research community can leverage these tools to advance research in various areas of natural hazards engineering. Through its emphasis on multi-hazard and multidisciplinary approaches, the Sim Center benefits the broad natural hazards engineering community. We foresee that policymakers worldwide will be able to rely on researchers' integrated simulations to make vital decisions to mitigate the social and physical damage from natural disasters, thus creating more resilient communities. For more information, visit the Sim Center website and join our community.
The Center for Geotechnical Modeling is located at UC Davis. The center is operated and managed under the direction of Dan Wilson and Ross Boulanger. The research performed at the center is to advance the ability to predict and improve the performance of soil and soil structure systems affected by earthquake, wave, and storm surge loading. This is done by scaling the stress in a model specimen using the radial G-field produced by a centrifuge. The main equipment at the facility consists of a 9-meter centrifuge shown in the lower left, which has the largest shake table in the world, and a 1-meter centrifuge shown in the lower right, which can be used for pilot studies. Both centrifuges are supported by a large and diverse set of equipment that can be used to build models. The facility is spread across 3 separate buildings, moving from left to right. The prep for the 9 and 1-meter centrifuge is done here, as well as housing of the 1-meter centrifuge. Located in the middle building is electronics and sensor calibration, and then finally over here on the right is the 9-meter centrifuge, which is located beneath the ground. For those of you who have not seen how a centrifuge operates, here is a sketch of the 9-meter centrifuge. The centrifuge rotates around this spindle, which is shown here in the center. As you rotate faster and faster, the bucket starts to tilt up, and when you get to 75 Gs, the bucket is near vertical. The G-field produces a normal stress on your model, and an actuator located down here at the base can simulate shaking of the model and any structures that you may have on top of the model. Here's an example of a recent project that used the 9-meter centrifuge. In this experiment, the system-level performance of building foundations founded on MICP improved zones overlying liquefiable sand deposits was investigated. This experiment was designed to understand the effect MICP had on reducing total and differential settlement. The study did show that MICP had an effect at reducing settlements and damage to buildings. Thank you for your attention. For any additional information about the center, please visit our website, which is shown here below.
Hello, everyone. I am Joel Conte, the PI of the NHERI at UC San Diego Experimental Facility, which consists of a large high-performance outdoor shake table, which was commissioned in 2004. For 15 years, we have used it as a 1 degree of freedom shake table. The table is now under upgrade for 6 degree of freedom capability. It will reopen in October 2021. And with the upgraded shake table, we'll be able to investigate in full 3D And at large or full scale, the combined effect of realistic near-field translation and rotational ground motions applied as dynamic excitation to structural, geotechnical, or soil foundation structural systems, including the effect of soil structure interaction, nonlinear soil and structural behavior, and soil liquefaction. You see here some large-scale and full-scale specimens that were tested in the last 15 years. Many building specimens out of reinforced concrete, pre-stressed concrete, timber, metal. You can see utilities. We can also use the shake table in combination with large soil boxes to test geostructures, such as retaining walls here and here. And finally, here we have the NHERI at UC San Diego team, consisting of a number of faculty members with expertise in various aspects of earthquake engineering, with 20 years experience in running this facility. We also have very talented research and development engineers and technicians ready to help you plan, design, and conduct your future experiments. We can be contacted at this general email here, and more information can be obtained on our website at the Design Safe. Thank you very much for your attention.
Hi, my name is Lori Peak, and I am the principal investigator for the National Science Foundation supported Converge facility, which is headquartered at the Natural Hazard Center at the University of Colorado Boulder. Converge was established in 2018 as the first social science-led component of the Natural Hazards Engineering Research Infrastructure, or NHERI. Our team consists of full-time researchers and graduate and undergraduate students here at the university, as well as a global network of partners from across many disciplines. Converge brings together networks of researchers from geotechnical engineering, the social sciences, structural engineering, nearshore systems, operations and systems engineering, sustainable materials management, and interdisciplinary science and engineering. We support and advance research that is conceptually integrative in an effort to democratize educational opportunities and the research process through a 5-step convergence framework. First, we identify researchers through connecting and collaborating with the 7 NSF-funded extreme events research and reconnaissance networks. Second, we are working to accelerate the education of a diverse next generation of hazards and disaster researchers. To that end, the Converge team has developed a series of training modules that cover a wide range of topics, including, for example, social vulnerability in disasters, disaster mental health, cultural competence, and emotionally challenging research. Third, Converge is dedicated to developing a research agenda for promoting problem-focused and solutions-oriented convergence research in the hazards and disaster field. Fourth, Converge works to connect and coordinate functionally and demographically diverse research teams. Converge has established the first leadership core for extreme events reconnaissance and research that brings together the leaders of the NSF Extreme Events Research Networks and the NHERI facilities that support reconnaissance efforts. Finally, Converge supports and funds convergence-oriented data collection, data sharing, and solutions implementation. We have funded researchers to study the impacts of the COVID-19 pandemic, the recent California wildfires, hurricanes, and other extreme events. These 5 key activities and the many other efforts of the Converge facility are designed to ready researchers to both assess and address the many pressing social, economic, environmental, and technical challenges that lead to disaster losses. For more information about Converge programs, activities, and publications, please visit converge.colorado.edu. Thank you.
The University of Florida proudly hosts a shared-use NHERI experimental facility that enables transformative wind hazard research. Our globally unique boundary layer wind tunnel is located within the 20,000 square foot Powell Family Structures and Materials Laboratory. The UF NHERI PIs and staff help guide researchers through the process of vetting project ideas, writing proposals, conducting experiments, and identifying outreach opportunities. The wind tunnel simulates atmospheric flow conditions at a reduced geometric scale. We have developed several features that dramatically increase experimental throughput. The terraformer is a unique system that controls the height and aspect ratio of more than 1,100 individual roughness elements, providing unprecedented granularity in the control and tuning of approach flow. In less than 90 seconds, the roughness configuration can be changed to alter the boundary layer profile and geometric scale. A suite of instrumentation is available to monitor flow velocity and test subject pressure, base reactions, and motions. Turbulent flow is measured using Cobra probes mounted on a 3 degree of freedom instrumentation gantry that can traverse nearly the entire length, width, and height of the wind tunnel. The gantry is also fitted with a stereoscopic particle image velocimetry system, or PIV. Its energy laser illuminates particles that are dispersed into the flow, while 2 high-speed cameras capture the particle motion to produce 3-dimensional, time-resolved flow field measurements. The simulation of non-neutral and non-stationary flow is achieved by our flow field modulator, or FFM. The FFM slides into the wind tunnel on a track system upwind of the terraformer. This array of over 300 individually controlled fans can produce non-monotonic flow profiles and impart transient gusts characteristic of field-measured extreme wind events, enabling new investigations in wind structure interaction not possible in a traditional boundary layer wind tunnel. Please contact us to initiate your wind hazard research. We're looking forward to hosting your NSF projects in our NHERI experimental facility.
The NHERI at UTexas Large Mobile Shaker Facility is located at the University of Texas at Austin. We are home to 5 large mobile shakers and associated instrumentation, including data acquisition systems, geophones, 3-component broadband seismometers, a fiber optic distributed acoustic sensing interrogator, 3-component nodal seismic stations, and cone penetration testing equipment. While our equipment is stored in Austin, Texas, our mobile shakers can be taken anywhere in the world to conduct in situ dynamic testing of civil infrastructure and natural geologic systems. These in situ testing capabilities are essential for evaluating existing infrastructure in actual field conditions that are difficult or impossible to replicate in a laboratory. The NHERI at UTexas science plan revolves around 3 main research thrusts. First, non-invasive subsurface imaging from 1D to 3D. Second, in situ liquefaction and nonlinear testing of soils. And third, soil structure foundation interaction and structural health monitoring studies. Some example projects include in situ nonlinear testing of bioremediated soils engineered to reduce liquefaction potential. Here, the T-Rex and Rattler large shakers were paired together to induce higher levels of shear strain deeper in the soil at a site near Portland, Oregon. Here, the triaxial T-Rex shaker was used to non-destructively test a bridge in New Jersey to characterize soil foundation structure interaction under large amplitude shaking. In another project, the shaker from our smallest truck was removed and mounted on a scaled building model to simulate dynamic loading on a structure atop a newly developed seismic isolator. For more details on our equipment and videos from past workshops, please visit our website at utexas.designsafe-ci.org.
The University of Washington in Seattle hosts the NHERI Rapid Natural Hazard Reconnaissance Facility. The mission of the facility is to provide investigators with the equipment, software, and the support services needed to collect, process, and analyze perishable data from natural hazard events. The facility emphasizes 3-dimensional, image-based, advanced survey data to serve a range of disciplines. Some of our most requested equipment includes tripod-mounted terrestrial LiDAR systems capable of scanning ranges up to 2.4 kilometers for landscape scale mapping, as well as smaller and extremely portable systems with a 130-meter range. The unmanned aerial Phoenix Mini Ranger LiDAR system, customized to meet the needs of the rapid and natural hazard reconnaissance community. 2 Street View camera systems with car and backpack mounts for post-disaster image capture. And a 2-meter-long autonomous survey boat for collecting bathymetric data. In addition to instrumentation, RAPID also provides reconnaissance advisory services and basic logistics support for field investigations. We respond globally to disasters and to field data gathering projects across the world, so we can help you get your equipment where it needs to go. You can find more information about the equipment portfolio, software, and services on our website at rapid.designsafe-ci.org. We are committed to reconnaissance-based science, shared resources, open data, interdisciplinary research, community engagement, and innovation to reduce the adverse impacts of natural hazards. Please don't hesitate to contact us if you have any questions about the facility or about what we can do to help your NSF project.